Okay, so in the second part here, what we will do is walk through, I have 4 examples for us to take a look at, and just see how that new rule that we have seen in the theory will work now in practice. So first example, we do have a polynomial. It is made up of 2 terms. So with any polynomial function, we can always differentiate term by term. So if I focus here then on our first term, this is where we now have to apply that new rule. We have an exponential function, base e. Here is our exponent, so we'll have to use that chain rule idea. So the first part is that we leave the exponential function. The derivative of the outer function stays the same. And our inner function is this exponent, so we now need to multiply by the derivative of the exponent. And now we can just use the exponent laws that we're familiar with. So the derivative of our exponent here would be 4x. Same thing will apply here. As I take the derivative of this term, we can leave the coefficient alone. We have an exponential function, so our new rule says that we leave the exponential function alone, and then we have to multiply by the derivative of the inner function, which in this case is essentially our exponent. We need to be careful. Reminder from some of our past experience here that I will rewrite that as x to the exponent 1/2 as I think about the derivative here. So as I take the derivative, we will end up with 1/2 times x to the exponent negative 1/2. I'm going to simplify here just a little bit. As we saw in the last video, typically we put the exponential function on the end. So I'm going to move the 4x first, e to the exponent 2x squared as our first term. Second term, I'm going to combine a few things here together. We do have a numerator and a denominator. In our numerator, 3e to the exponent root x, and my denominator will have that too. And as I shift that down as well, we will have the square root of x. And I'm going to leave the function like that. I'm not going to try to simplify it any more than that. In our second example then, again, the idea is that we can start to combine this new rule with some of our rules that we already know. In this case, we do have a product of 2 functions. We have x squared, and we have that exponential function. So I'm going to have to use our product rule here. So as we run through this with our product rule, we would say then f prime at x equals, same as always, derivative of the first function is 2x multiplied by the second function, e to the exponent x squared. And then I would multiply the first function, x squared, by the derivative of the second function. And then again, this is where, as we take the derivative of this exponential function, that we're going to have to apply that new rule. The outer function is e to the exponent x squared. So the exponential function stays the same, and then we take the derivative of the inner function, the x squared, so we end up multiplying by 2x. Simplifying here a little bit, the first term I'm going to leave alone. The second term I can reorder some things here as I collect them together. So I could say that this is equal to 2x cubed e to the exponent x squared. If we want to try to clean this up a little bit more, we can also common factor here. 2x is common. I have an e to the exponent x squared that is also common. If I factor that out of the first term, we're left with 1. And if I factor that out of the second term, we would be left with an x squared. In our third example, this is where we see all the x's and y's being mixed together. This is something new that we learned just before March break. Okay, this is implicit differentiation. Okay, so remember with implicit differentiation, we differentiate term by term. We just need to be careful that whenever I differentiate the variable y, we always have to multiply by dy by dx. So in this case, the x and the y are being multiplied together in the exponent. So we'll get to differentiating x and y in just a second, but we start by differentiating the outer function, which is this exponential function. So the derivative of the outer function is just e to the exponent xy. And now I need to take the derivative of this exponent. And again, in this exponent, we have to deal with this as our product rule because we have 2 separate variables. So I would say then the derivative of the exponent using our product rule is derivative of the first. And I'm going to write it in here just so we can see each part. Once you get good at this, you don't need the 1. I'm going to say derivative of the first is 1 times the second function is y plus the first function x times the derivative of the second function. The derivative of y is 1 multiplied by dy by dx. So there is the derivative then of just that first term. From there then, moving on term by term, minus derivative of x is 1 equals derivative of 1 is 0. If we expand then this into the brackets, okay, my goal here in the end is to try and isolate the dy by dx. Again, I'm going to put the y first and then the exponential function second. So y times e to the exponent xy. Similarly here, I'm going to say that we have x times e to the exponent xy dy by dx equals 1. We can move this term to the right-hand side as well. So x e to the exponent xy dy by dx equals 1 minus y e to the xy. And then lastly, dividing out that coefficient, derivative then dy by dx is equal to 1 minus y e to the exponent xy all over x e to the exponent xy. Our last example then goes back to our very first unit when we first started learning about derivatives. Reminder that the derivative is a rate of change, or it is also the slope of a tangent to any curve. So one of the first examples that we started looking at was this idea that could we come up with the equation of a tangent to any function. So it's that same concept that we've looked at since our first unit. The only difference is now that our function can involve these exponential functions in it as well. This idea we could have e to the x over x squared. So if I want the slope of the tangent so that I can get the equation of a tangent, my first step then is the derivative of this function. So f prime at x equals, and here then again we have one of our old rules. We have our quotient rule. So we have the derivative of the numerator, derivative of e to the exponent x. This is just e to the exponent x multiplied by the denominator minus our numerator multiplied by the derivative of the denominator all over our denominator squared, or x to the exponent 4. At this step here, we have 3 terms. We have this, this, and this. So I'm looking at, can I reduce? Often we can reduce something with that denominator. In this case, they all contain 1x. So I'm going to reduce these all by 1x, leaving us then with x e to the exponent x minus 2 e to the exponent x all over x cubed. And like we did above, we could do a little common factoring here. E to the exponent x is common to both terms, leaving us with x minus 2 all over x cubed. So there is our derivative. That's the new piece. All the rest now is stuff that we have seen before. If I want now to come up with the equation, we need to remember again that I need the slope of the tangent. Okay, so we can say then, therefore, f prime at 1, okay, there's the point where we want the tangent. So f prime at 1 is equal to e to the exponent 1 minus 2, all over 1 cubed. If we evaluate, we get negative e. Okay, again for our note, just a reminder that that is the slope of the tangent. Once we have that, if we want to find the equation, we can then take the slope, which is negative e, and the point that it passes through, which in this case is given as the point 1 and e. We can sub those into y equals mx plus b. We would have then, therefore, y, which is e, equals m, and x, which is 1 plus b. And if we rearrange here, we will end up with b equals 2e. So we have some interesting values. We have a slope that's negative e. We have a y-intercept that is 2e. So our equation will look a little different than what we would normally see, but we can still write it out here. Y equals m, so negative e, mx plus b, so plus 2e. There's the equation of the line that is tangent to the curve f at x at the point 1e. Hope that helps. If you have any questions, don't hesitate to send me an email or post questions on our classroom. And good luck with the assignment. Have a good day, guys. Bye.